So this is part 2 of the discussion of first order linear differential equations. Time ran short in the first video where we introduced them and tried to go through an example. We actually completed the example, but let's kind of review and write out some steps here. So the first thing is what a first order linear differential equation looks like, and we can use any of our notation from derivatives. Let's see what we can do here. We'll write it out here. You remember there was a function of x so first order differential equation means we will see a y and a y prime probably. We won't see anything greater than a y prime. Linear means that the y and the y prime are added. They're not multiplied. And the template we want to get everything in is we want the y and the y prime on one side. We definitely want 1 or nothing in front of the y prime. And if it's cleaned up in this way, and where you see the p, there are nothing but x's there. I mean, there can be numbers, but there can't be any y's inside of that. And same thing with the q, then we have it. So if we want to kind of write out some steps, basically step 1 would be match the form. So make sure our y and our y prime are on the same side, and there is nothing in front of the y prime. And you want to clean things up as much as possible. So let's see, what do we do next? If that's the case, we're going to find p of x, which if we've got it written correctly, it'll be right there. I mean, it's not hiding from us. And then we will find, once we have p of x, we will find the integrating factor, which is e to the integral of p of x dx. Okay. So we have our equation in the correct form. We're going to identify that p of x, which will be in front of the y, because everything's in the right form. And we're going to use it to get the integrating factor. Then we will multiply all terms, let's say parts, by the integrating factor. That's left and right. And we should say here that we will clean up if we can. We don't want to mess. That integrating factor could look like anything. Once we integrate, it may look like something nice. It may look crazy. We may even have to use some very difficult methods to integrate something depending on how crazy it is. So we said once we got that far, and we kind of have to have an example in front of us, but we said that if everything is correct, the left side what in the world is that word? Let's start over. Left side integrates let's say like reversing the product rule. So while there's an addition, so there's two things on the left, normally you would think of that as a sum difference rule and try and integrate them separately. But what we'll see is the combination of those two things together really reverses a product rule. So u times v prime plus v times u prime. We will integrate right hand side. And we'll also say, remember, Because we're doing something new, it's easy to forget. Plus c. So basically we get a plus c on the left hand side, we get plus c on the right hand side. We can move them to the same side and be okay with that. Okay. Let's see if we can make this a little bit smaller. I don't know, I don't think you want to lose that. That won't look good if it's hiding. So let's try and work through another example in the time that we've got here and kind of make all this happen. So I'm going to pull another one from a textbook, but it'll look like x times dy dx equals cosine of, let me change that a little bit since I'm going to be making a fraction here. Cosine of x over x minus 2y. So the first thing to notice is it does not fit the template that we have. It does have a y and a y prime. They're not multiplied or anything like that, so we could get them all on the same side. So let's start by doing that. Let's keep the dy dx expression on the left hand side, and let's move the y expression over, and then we will still have the other part of the right hand side. Now there is a problem here. What's in front of the dy dx is not 1. So it's very tempting to just go ahead and see the 2 in front of the y and call that your p of x and jump to your integrating factor. But let's go ahead and kind of work it out. So what we did here was, if we're matching the steps over here, this was step 1. We matched the form. Well, that's still not the match form, so let's kind of mark that out. So we're going to divide by the x. So give me 2 over x. Now unfortunately over here on the right hand side it's making things worse, excuse me, the x squared in the bottom. So when we look at this, now it does match the form over here where this 2 over x is our p of x. And the q of x is on the other side, but that's kind of irrelevant. We're not doing anything with it right now. So we've got to do our integrating factor. So we're going to take e and raise it to the integral of 2 over x dx. And if you're paying attention to that, that would be 2 natural log. Ooh. Let's clean that up. 2 natural log of x. And that is very tempting to just call that 2 or 2x. But remember your rules of exponents. First of all, the base e and the natural log exponent can't cancel out if there's something in front of it. So we're going to have to move that 2 inside. So you may remember a rule that said you can move this 2 in as an exponent. So that's what we do. And then we do have base e raised to the natural log, and that is a straightforward rule that makes this x squared. So that is our integrating factor. So kind of backing up here, we made it match here, and then we identified our p of x, and we found the integrating factor. Now we're going to multiply both sides by that integrating factor. So let's see here. We're going to multiply, we'll have x squared times dy dx plus, well, I guess the color is not really important here, is it? Well, I guess I could go ahead and write it. X squared times 2 over x y equals, and then we'll have x squared times cosine of x over x squared. So we did go through and we multiplied everything. Now this is where you see a huge advantage in cleaning up. So let's rewrite it. X squared dy dx plus, this will be just 2x. One of those will cancel out. And then the x squared will cancel out over here, cosine of x. That is still my step 3. So now let's actually try the integration. Okay. So now we're going to take and we're going to integrate the left, integrate the right. But as I said, this right here is a u prime, u being x squared, u prime being 2x, and then we can call the other one y being v, and dy dx being v prime. So we don't, like I said, we don't want to try to integrate these separately. We're just going to go ahead and treat it like we're reversing a product rule. Aren't you glad you finally got that? So now that gives us u times v. And if I want to integrate the other side, the integral of cosine is sine x. So there's a plus c. So we could stop right there if we're okay with that. Let's see. Let's kind of match up our steps again. So the left side integrates as the product rule. So there we are. This right here is step 4, and I said that the right hand side, go ahead and integrate it and put a plus c with it. So there's step 5. If you want to take it one step further, you could write it in a common form with y by itself, which would be dividing by the x squared. Usually, well, not usually, but if you continue in differential equations, you will find that they are dramatically more difficult as you move on. So this might be one way to write a solution by getting y by itself. You can always leave it up here. But another way that they're written, is sometimes instead of getting the y by itself, because if there's a higher power or something else is going on, it might be more difficult. You could get the c by itself, because usually it's just plus c. So it's fairly common to see answers written with the constant by itself. So if we went back to our first solution here, we could move the sign over and we'd have x squared y minus sine of x equals c. Oop, what in the world happened there? But that's 3 different ways you might see it written, depending on how difficult it is to get y by itself or c by itself. Okay, we'll go on and do another example in a moment.